Okay, so this is my first perspective seminar, so you'll have to bear with me. All right, so why should you listen to me? I currently work at Fugo and I'm the modeling automation team lead, which I happen to think is a pretty cool job. So I work with 6 other very skilled individuals and we all kind of refer to ourselves as data scientists. So we work at that intersection between maths, research, and software engineering. So today I'm going to talk about how I got there, so my education and career, and particularly the cool things and the problems I've worked on. As a side quest, I'm going to talk about the things I liked and didn't like, and the way I kind of ricocheted between different jobs, because we don't all have a lovely career progression and a plan for where we're going to go. So here's my background, and first disclaimer, I didn't do maths. I did a Bachelor of Mechatronics, and I did that at QUT as well. So if you want to boo me or throw something, feel free to get it out of the way. But while I was there, I did a lot of cool summer intern things. So I did one at CSIRO, and I would like to encourage you all, if you get the opportunity, to look at summer opportunities. They're really useful in finding out what goes on after and potentially even getting jobs or career opportunities. And I also then did a PhD here. So at CSIRO, I worked on a project, and my project was computer vision for an autonomous underwater vehicle. So Starbug, the yellow one you can see up the top. So the concept behind this project was, what if you have a vehicle that you want to dock with, or what if there is bad weather and you need to power down? So you want to hold on to something so you can turn your engines off. The other application was potentially if you want to distribute some sensors around. So you might have these sensors attached to target poles, and Starbug can go move them around so you have a nice distribution. Now, I was very lucky that there was a paper that got published as part of this. And it was a really good opportunity for me to see how that whole process worked. Now, the first approach, and that's the one on the bottom left, is what I did. So my approach didn't end up being the winning approach. So first off, I approached it with some image cleaning up. So Gaussian filter and histogram equalization. So that's trying to get a crisp and a clear image. And then a Huff transform, which is trying to detect lines in an image. And then looking, so once you have those lines that are potentially your target poles, trying to find those light and dark patterns on it. And then the ratio between them, think like a barcode, will be able to encode different targets. So you might have one for your vehicle, you might have one for your sensors. Now, the other thing we did is, because it was, so you have multiple frames in your video. So once you've detected one target location, you want to try and track that over time. So to do that, we used a Kalman filter. Now, as I said, my approach, which I initially did in MATLAB, great. Once we transported that onto C++ and put it on the vehicle, it was way too slow. So we only managed to get like 1 hertz, so one frame we could process a second. So that's kind of a good example of the 2-language issue you often have in coding. So you might want to use one language that's really fast to develop in and find out what's going on, and then another language that is harder to code in, but will operate more efficiently on hardware. The beauty of Julia is that we don't have to do that. So you can use it to develop in. It's a high-level language, and it also runs very fast. Now, the image on the bottom right, so that's from the paper. So this was the final solution. And here, rather than doing an expensive Huff transform, we basically applied different templates. So we would search through the image. It was a lot faster. All right, so now my PhD, which was entitled Statistical Analysis of Orientation and TDOA, Time Difference of Arrival Based Geolocation Estimation. So the best example of that everyone knows is GPS. So if you have a look at the middle one, you've got the pink triangles are the satellites, and then the green is Earth, and you're on Earth somewhere. You have your measurements, so your time, which you can turn into a distance that you've received from those satellites. And you also need to approximate the clock bias. So you're trying to calculate for those variables, your X, Y, Z, and then your clock offset. So that's how the GPS works. But some of the problems with GPS, which we investigated in my PhD, was when you can have an estimate that's really poor. And how that can occur is that case on the right. So if you have all of the satellites due to noise, those lining up roughly, your estimate shoots off out to one side. So you get a very poor estimate. The other thing down on the left that I did was looking at the cases where you do have one solution versus you can have multiples. So deriving the equation for that boundary. One of the things in my PhD, I realized that I really enjoy the programming, the simulation, and the maths, great as it is, isn't really the be all and end all for me. So, and how I came to that realization was during my PhD, I did a lot of part-time work. So my PhD took 7 years. I also had two children during my PhD. And the things I worked on part-time, to one, get a decent amount of money coming in, and to learn about the world. So I worked at Shell, which is oil and gas company, or QGC. So there they have their wells that produce gas, and they needed a new forecasting system. So they wanted to be able to say what the curve for their well production and then forecast that. And then you have constraints on the system. So you might have pipeline constraints in terms of being able to export it. So from the combination of all those different elements, being able to forecast how much gas they're going to produce so they can make sensible sales. The other interesting one, two more, was that systems reality. So if you have these big, long mining trains, they have brakes on them and they can have leaks on them. So they're really long trains. They don't want to have to go around with their little microphone and listen for the leaks. So what they would do is they'd have a wheel sensor and then a microphone, and they'd drive the entire train past. And from that data, so you've just got the ticks from the wheels, and from if you hear the hiss of the leak, they wanted you to say, oh, it's in carriage 3, 2 meters down. So as part of that, you're trying to work out from those wheel sensors, one, how fast it's going, and then to match that with the different carriage configurations. So they'll have certain spacing in the wheels. And from there, you can work out the answer. One of the other part-time one I did was for calculating the particle fragmentation curves. So this was if you have a mine where they have the big area they're trying to blast away and get the ore out of the ground. So once you put the explosives in a certain pattern, you can predict the size of the pieces of rock that you're going to get out of it. So doing that modeling, well, taking the research and the paper and turning that into actual code that they can run and deliver and sell. So I had finished my PhD. I'd done all this part-time work, and I decided I wasn't going to stay in academia any longer. And first off, I went to QSuper, which is a finance company. So one of the joys of that was it was very flexible. It was 3 days a week. It paid very well, but the work itself wasn't quite my cup of tea. So I stayed there a little while until I got a better opportunity at Boeing PWI for Phantom Works International. And there I worked on some computer vision, but I have a video. See if I can get it to work. Hopefully it'll work. All right, so this is back in the oil and gas space. So because the wells are distributed all around outback, normally they have to survey them. They have to check them at certain regular intervals. And what they can do is they can send someone out in a car, but it's a risk because road fatalities is one of the major issues. But rather than doing that, you can use a drone. So you can send that out to inspect it for you. Now, the initial pilot that they did was remote controlled. So they had someone driving it, zooming in with the video and answering the inspection questions they needed to answer. But the idea behind the work I was doing was, can we automate that? So rather than have someone checking, we can set up the wells you have to visit. So there's your traveling salesman to survey them. You want to take your photos as you're over the top and then answer those questions automatically with computer vision. It's really cool how they catch it. I like that bit. Right. All right, so the questions we wanted to answer from those pictures were around the safe containment of the wells. So they needed the fence to be whole and complete, so we didn't get cows going in. We also wanted to know if the signs were on the fence. Now, if you've got a top-down image, you can't really see if the signs are on the fence, but you can see if they've fallen off. So that question became, can we see any signs that fall off? The other questions were around the infrastructure itself. So the hose from the well to the tanking containers, as well as to the pipelines. We wanted them to not be caught up on each other and kinked up. And then some questions around the lever arms themselves, so what position they were all in. And preferably checking if there was anything leaking. All right, so one of the things I learned from this opportunity was how challenging it is if you don't have a large amount of data. So because they were doing this this surveying remote control, we only had, I think it was 100 examples that were captured with this automated process. And 100 isn't a very good sample size to pick up when these things happen in 1 or 2 cases. So being able to have a decent sample size is really important. And potentially having a human in the loop. So let's say you can pick up 99% of the cases and you can flag, oh, this one looks a bit funny. You send it to an operator to look at. All right. Now, I did go to Fugro next and then Origin and then went back to Fugro, but I'm going to talk about them in this order. So Origin Energy, another oil and gas one. This time on the happy side of the fence, so trying to find and reduce the emissions. So they have a Picaro truck, which is their survey vehicle. So they have different sensors on it. So they have a lot of weather data as well as a parts per million sensor. So the truck itself can drive all over the fields, but if it picks up a reading, it will try to circle the emission source. So once it has the weather data as well as those measurements, it can predict the plume and give you a flow rate. So that's good, but the Picaro truck didn't pick up all the sources of emissions. So we'd have some data from that, and then we'd have some data where it's been picked up with someone's sensor. So you see I've got a sensor on the top there. So that will tell you a parts per million as well. And you can do a calculation based on what that value is at a certain distance from the lead. So we had a whole load of different data. And this is a very stereotypical data science, data munging type job where you have lots of different pieces of information and you're getting asked by the business generally, tell me this, what's going on? So the questions we were seeking to answer were around, okay, so which fields are we having lots of problems in? And potentially, can we pinpoint types of equipment that is causing us issues? And in a really nice way, they would really love if you can just predict and tell them if they're going to leak in advance, which wasn't really possible. All right. The other thing I did there was around how I handled the data. So you could use a SQL query to pull out the bits of data you wanted, but it was really slow. So if I wanted to pull out the data for all the wells, I had to set it running and wait 3 days and come back. I didn't like that. I'm not a very patient person. So rather than do that, I made a lovely little serverless application. So it had Oh, how much? So rather than having it running on one piece of infrastructure, you can have it running on a lot of things in parallel. So I created a table that basically referenced where all the data was. And then I would kick off. So for each of the wells in parallel, go and get the data you want, work out the information and give it back to me. And then I could just write those summaries. So it went from taking 2-3 days to 5 minutes. That was cool. Yeah, okay. So then, and now I'm working at Fugro, which is the world's leading geodata specialist. And together we create a safe and livable world. Now, I really enjoy that. And I do enjoy Fugro. And we're in lots of different markets. So it's a huge global company. I generally work in the energy side of things, but we also have a big marine business as well. And they are doing some really cool autonomous vehicles there. And I have a video of that one too to show. Oh, is it going to work? Hopefully. It worked. All right. Reminds me of my days at CSIRO. So they literally have the little ROV that goes off, as well as the surface vehicle that controls it. It's pretty cool. Now, Fugro has different lines of business. So we generally talk about the site characterizations or the asset integrity. So your site characterization is, where am I going to put this piece of infrastructure? So if I'm going to build a wind farm, I need to look at what's on the surface of the under the sea, and I need to work out where I want to put that big wind thing. I generally work in the asset integrity and land. So we work on different things. Oh, it's still going. Yeah, so inspection. Here's what I work on. So Rome's was initially spun up as part of Ergon. So it was a Queensland based startup. So we are trying to find power lines and infrastructure. So we want to find the poles and the wires, and we want to tell them where there are issues they might need to go and remedy. How we do that is by flying a plane that has a LiDAR unit on it. So it scans down, sends a laser, and you get a pulse response back. And from that, you can construct a point cloud. So you see the points now. And from those points, you can attempt to automatically model your infrastructure. And then you can tell them they need to go cut trees down, or they might have cross arms that have fallen down. So we have a crazy amount of data. We do our processing in the cloud, and we also have a human in the loop. So we have the humans to check our automation, because we are not perfect. The problems I've worked on in this area are in terms of finding the power line infrastructure. Once you've found it in your data, you have the client tells you where they think it is, and you have to try and reconcile the two. We've also worked on some engineering modeling. I'll talk about that a bit later, and we're now expanding out into classification and modeling. So here's two examples. So the green might be what we found when we've scanned and modeled the network. So the circles would be the poles, and the lines, the wires between them. And the red one might be the client schematic. So how are you going to match those two? It's a classic maths network matching type problem. But we also need to work out how we're going to handle cases where things don't line up nicely. So let's say you've got in the client schematic, there's one bay, but you found two bays. So how do you handle those sort of edge cases? We also need to shift and align them. As you can see, that they're not quite measuring up correctly. And then there are cases where you might have one branch of the client schematic is off in one direction, but when you found it, it's slightly more over a different direction. Okay, now this is one of the cool engineering-y kind of things I've worked on. So let's say we have our wire and we have our poles, and we want to work out what are problems that that wire can come in contact with. But we only have that wire as we've captured it. So we only have it when it was flown at whatever current, whatever wind, whatever temperature it happened to be at. So we want to try and work out the risks involved in different scenarios. So we might want to know, okay, so we captured it today, it's winter, but in summer, how close are we going to be to different objects? So let's say we captured it today and it's what, 12 degrees it got down to. But we want to know 35 degrees or even 40 degrees in summer. And what's going to happen is it heats up, the wire is going to sag. So we need to work out and solve the maths for that based on our engineering properties. And also, let's say we've got the wind blowing, so it might move to one side. So we then have that complete surface. So you've got, think about it as it's kind of sagged and up and then kind of swung out and around, like a banana. That's why I call it the banana model. And we want to work out. So let's say you've got then, so you've got that shape and you've got your building. You want to work out the closest approach between those two modeled objects. So again, kind of cool math. All right, okay. So one of the biggest problems with this wasn't just solving it, it was optimizing that solution to be really efficient such that we could calculate it and afford to calculate it efficiently. So being able to do the maths equations for how this works is step one, but being able to test it locally and verify it works is step two. And then step three is to test it at scale so that you know that you're catching all your different edge cases. And now we're kind of branching out away from just power specific. So we are looking at the LiDAR data itself and all the different objects we can potentially model. So I'm going to show some data. Oh, whoops, I should have kept that to later. All right, so here we go. All right, so here we've got some data and I've turned it black so you can't see the answer already. And if you have a look around it, it's not that easy to tell what's what. Now, we do have other information. So if you turn on the point source ID, we can see here, these are the plane lines as you scanned across. And you can kind of see in the data, the lines from the scan angles, sort of see the lines there. So that's from the laser as it scans across as you're going across your flight line. Now, here I've got the return index. So this is, once the laser shines down, it can reflect off, say, the tree leaves, and then it will penetrate potentially and reflect off the ground surface again. So the return index is the number versus the total returns. So it might be the first return and it might have two, one on the tree and one down on the surface ground. All right. Now here's our classifications. So I'm going to attempt to be interactive and call for audience participation. If you had this data and you were trying to decide what things are, what are some ways you could attempt to do it? So maybe I'll turn the point radius up. All right, so let's pick one of the classes. So we'll go do vegetation. Okay. So let's say you're trying to, buildings is probably easier. We'll talk about buildings first. So if you had this data and it's just XYZ position, how would you attempt to work out what's going on there? Anyone at all, except the people at the back that know the answer. Yeah, you can ask a question. Okay, so the colors are artificial. So they're what our modeling has already determined. So we've gone from the black, put the black back. So from just those points, we've come up with labels for them. So our automated methods have tried to decide which points are most likely to be building, which points are most likely to be ground, which points are most likely to be vegetation. Now, if I give you a slight hint, let's say we're looking at this patch of points here, this group here. And you just pulled all those points together. What properties? Yeah.
Something about the flatness and stuff.
Yes. So one of the things we do is we pull in the nearest neighbors. So you might, for your point, grab all n number of points around it and look at the properties of that group of points. So they might be particularly flat, or in the case of vegetation, they might be more fluffy looking. So that's certainly one of the things we look at. Let's say we were looking at ground. So one of the things we can look at there is, well, is it the last return? We don't tend to get stuff going through the ground. That's a good giveaway. Points that are very low also tend to be ground. Yep.
This line, see through the building.
No, so it won't go through a building. It can sometimes go through a window, interestingly enough. You can get through and get a little bit in the room.
So what's the yellow stuff?
Oh, sorry. So if I zoom out, yellow is my background of the, so that's the void. All right. One of the more challenging classes we've been working on is road. So road is very similar to ground. That one's hard. Also working on vehicles. Now, the other thing is once you have a rough idea of what points what, so you might use some features like if it's flat or if it's low to decide what class you think it might be. To get it very clean like that, you need to do some modeling to clean up. So effectively, you might want to model buildings. So once you have a group of points here, you could attempt to construct a 3D model. So you could define the flat surfaces and their perimeters, and then everything that isn't within the model, you don't want to be classed as building. All right. So I used to be a data scientist, but now I'm also a team lead. But as a data scientist, there's a lot of different bits and pieces I've learned that's super useful. So I would highly recommend courses like this where you do lots of software development. I think it's super useful if anyone's going to go out into the real world, which you all will at some point. You need to be able to implement and use the knowledge and the maths and the algorithms that you've worked on. I've done a lot of different programming languages. I do really like Julia. I think it's fabulous. I've done a lot of cloud computing as well, and DevOps. That's all very useful if you get the opportunity. I didn't do much coding at university, but you pick it up as you go along. And now I am a team lead, which is another set of skills I'm learning. So I guess the takeaway from that is that we are all ongoing learners. All right. And then the last slide I have was around the summer program. So Fugro does take students over summer. So if anyone's keen, we will be advertising for a student or two. We're a fun place to work, aren't we? Yeah. So the top left, we have Avit there. So he's our principal engineer. So that was from when he had been 10 years at the company. And down the bottom, you can see we celebrate birthdays very well. We have a foosball table, which is also a good selling point. And we go for drinks, also important. All right, well, that's all the slides I have. So if there's any questions people want to ask, yeah. Yes. Yes, that is a very good question. So water is one of the things we want to model and work out. Now you can get different responses. So if the water is very flat, the signal can like bounce right off. So you might have no points because you get no return from it. If it's wavy or coastal, you'll often get a couple of scattered returns. But because you don't know which it's going to be, it can be a very hard one to detect. And also tidally. So let's say you've flown it with the plane once at one time, and then you fly it later, you might have two different water levels as well. So it can be very tricky. Yes?
Just another question. Do you ever have like they seem to have values that more ranges that for example, road that quite flat. Do you have road that's detected as like or something?
Yes. So the way we're currently handling classification is we're going for binary classifiers. So we're trying to split it up into it's either this class or it's not. So you might have your road or not, you might have your ground or not, vegetation, building. But then once you've run all of them, how do you decide which one? So let's say two of those classifiers, ground and road, they both think that that point is theirs. So how do you resolve which one it is? So there's probabilities you can look at, and also then the final modeling tends to be the way we make those decisions. Yeah.
Modeling, is that like relating it back to the maps we have?
Yeah, so when I use the generic term model, I'm normally talking about a mathematical representation of the underlying object. So you might have a building and I can represent that as like a footprint, and I can represent it as planes that are for the walls and for the roof. If you're talking about the road, you can represent that as a center line and a width. We don't pull in external data. So let's say you've got your Google Maps where it has those road polygons. You could just pull those in and use them to classify road. We don't do that because we can't get that for everywhere, and it has to work everywhere. Edge cases. Yep.
When you have the slide of the schematic versus the data you guys got, why was it so different?
Well, that is actually a very nice case where they're not that different. So unfortunately, a lot of this infrastructure was put in ages and ages ago, and they did it probably to the best of their abilities when they were surveying it to note down where it all was, but it's not as accurate as we would like. Yeah. Is what, sorry? I don't know. Yep. Yep.
With that, how does it get resolved? Do you kind of just say this is the new schematic? Or
Yeah.
like,
So ideally, we feed the data back to the client to say, actually, you got it wrong. Can you move it all? But clients sometimes don't like that, being told they're wrong. So what we often display is okay, so here's what we captured and here's what we found. And we will basically get rid of their network model. But what we'll do is we'll tell them, let's say this one here, we'll give it the same number as their asset number so that they can look up in their systems. It might have something special about it that they need to know for their information. And then if they send a truck out to it, they use our GPS locations. Yeah. Yeah. So we do a whole spread of things. So we'll have support tickets, which is something's broken, someone needs to fix it. We'll have kind of shorter term software where it's more, we already know what we're doing and we've got to go implement it. And we'll have more longer term research type projects. So let's say we want to add a new point classification, another like vehicles, say. We'll have to send someone to spend a while reading the papers, having a go, doing lots of different approaches. And that can be quite open-ended. And then we'll want to productionalize it once we know we have an approach that works. We have stand-ups. We operate in an agile manner with tickets and Jira. We have Git for version control. Yes?
Do you like coding, like when you first came across it?
So I did like it when I first came across it. And to me, I liked it because it's very logical and structured. It has the elegance of a mathematical solution to me. And there's differences across languages. Some are more elegant than others. But I have liked coding. And I know, sometimes I feel a bit unique in that regard, but everyone should like programming. Yes. Yes. Probably the one I can say is all the CDK TypeScript stuff. So that's the deployment language that you use for your AWS infrastructure. So it's a language which you tell it what things to build and what properties they need to have. Anyone going to object to that? The back? Nope. No one likes CDK? No. Yep.
Why did you,
Sorry?
what made you decide
What made me decide
to leave academia?
to leave academia? I think when I went and did my PhD, I wasn't like, my idea was that I was going to go to CSIRO anyway. So I was never really intending to become a lecturer or a professor. So it was more a natural progression of where I was going. And probably a combination of the fact that the just by myself writing out maths and lots of equations was less interesting to me than the simulation and the programming side of things. In combination with all the part-time work where I really enjoyed being able to deliver and show progress and build a thing that did something, I find that very rewarding. Yep.
Do you use machine learning?
Yes, we do use machine learning. Yeah, we use a lot of clustering algorithms. We use a lot of XGBoost, random forest, a lot of maths as well, pure regression and other bits and bobs. Yeah. We do use UNets, bit of neural nets, nothing too crazy. Sorry, go on.
How do you explore neural nets in your work? Like, what are the drawbacks of using them?
Yes, so we've tried to use neural nets. So let's say you've got your point cloud and the neural nets don't natively operate on that. It's kind of very sparse, the data. So you need to turn that into an image. So what we have done is divide it up into a grid, and then you can choose like the maximum height point in that grid and create an image that way. You can also do multiple layers with embedding different information in those from that voxel itself or that pixel. The problem we found with the UNet is it was expensive to run, and we didn't get any better results than the other approaches we'd used. Yep. Yep. So normally we come up with a little project that you can tackle, and a lot of the basics of how to work in a software organization like Git, how to use Julia, how to do a pull request, how to write tests would be the main focus. We don't necessarily expect you to come up with something super useful for the business. You're mainly there to learn. It's a learning experience. Yep.
I don't know if it's all relevant to the end, but parenting and having the full time.
Oh God. Yeah, it's an interesting question. So I have recently, with the new team lead role, gone up to full time, whereas I was 4 days a week. I am finding that a bit of a challenge. I think it is a hard juggle. My husband also works. So having the ability to, my kids are in primary school, but they still need a little bit of help. With the remote working, it is easier in a sense. So we can alternate being at home to be around them for the before and after school. But it is a challenge. Yeah.
What is your average day at work look like?
Yeah, so I tend to start early because it's quiet and I can actually get some code done a lot of the time. And then we have meetings. So I have a stand up where I'm in a meeting with all the other team leads in my area where we just talk about all the big blockers or important things that we might need to call out for help across teams. Then we have the individual team stand up. So that's where we all touch base, how we're doing and how we are either going to work on the things that have been cascaded down or what we're doing for the day. Then if you're one of the people in my team, you predominantly get the rest of the day to code and learn stuff, look at PRs, have lunch. I get pulled into a lot more meetings than I would like, but yep.
How do you like particular project?
Yeah, I must admit, I really enjoyed working on this one. For me, it was the great combination of my engineering roots, as well as the really solid maths and a software problem to solve. So I've really enjoyed that one. Yep.
When you decided that academia wasn't for you, when did you decide this during your PhD?
Yeah, well, there's a lot of PhDs in my team, and you ask any of them, do you recommend a PhD? And the answer is always no. I think they can be a bit of a hard slog. Not that there's anything wrong with that, and there are lots of lovely lecturers. Sorry.
Lots of other people in the PhD program, so like kind of deciding to move away, or they first do what you know.
It's not unusual for people to hang around more than I did, but most of the good people move away. Yep.
Which part of the LiDAR project are you part of? Like what are you responsible for?
Yep. So I'm responsible, once it is already in this point cloud format, to do the first automated pass. So there are different teams. So there's a team that's responsible for the planes and flying it and capturing that raw data. There's a team that's responsible going from the raw data, which is the waveform return signal from each of the pulses, to the point cloud itself, which is a task and a half. And then there's our team that does the first pass in an automated manner. And then we have another team that is responsible for the tooling for the humans to go in and fix anything up we got wrong. And then finally, there's the insights side of things, which is the further analytics on at the end. So once you've got all these useful models and important values, how do you communicate that nicely to the customer, the reports you make?
What this first pass?
So we will do our best attempt with the at scale in the cloud with the automated algorithms that are run, but then the humans will fix up anything that is incorrect, which is only a little bit.
I feel like identifying which parts of the grammar.
No, so we will do this, and let's say if I zoom in on something, let's say, that's not actually the right screen. Right, so let's say here, we'd marked this thing as a tree. It's the automated process. So a human will come and say, no, that's a car, you're wrong, and fix it up. And similarly, if you've got your poles and wires, if you might have missed a wire or the pole might not be at the right position, they might fix those up. Yep.
You mentioned before unit specific.
Yep.
How much data do you have?
Squizillions of data. Petabytes of data, petabytes. And it costs a lot to store in the cloud. Yes, you know that.
I think it's interesting, the industrial nature.
Oh, yeah, it is. Yep.
I find the LiDAR to be like really expensive. Even just like a little handheld scanner, like 10 grand. Like, do you know how much those aerial LiDAR scanners?
How much does the unit cost? The 1560i? I don't know. I would. Oh, there you go. $250,000 from the bat. Yep. As in, once you've got the discs out of the airplane, so you've flown it.
Yeah. So
Yep.
you've got the endpoints and
Yep.
stuff. How long does it like come up with a result?
So to run the classification pipeline itself. So because we are operating in the cloud, we can parallelize. So if I zoom out, we can see there's actually different files making this up. So what we do is we split it up and operate on a small piece of data at a time. And we do that across many, many compute nodes. So we can, in theory, it will only take as long as the longest tile would take. Hours, at worst. Yep.
After you process this data, who uses it?
Yep, so the point classification or the RSNM work stream is often the clients can be government. So they might want to know what's going on in their area and district. They might want to know where all the buildings and roads and things are. When we do it for the power line companies, the client will be the Ergon or Energex directly. Yep.
So when you guys actually scan it, it's not just you guys scanning and then work once last and stuff. It's the
No, so we are contracted to acquire, process, and deliver the results. And generally, the client likes to maintain ownership of the data. Yep.
How do you balance wanting to have this like really amazing model and great outputs, but also like having the client deadline?
Yes, so the client deadline bit, not so much, but in terms of balancing the amount of dev time we can afford to spend and wanting to get it as good as we would like, that's quite challenging. But we do have people, product owners, etc., sitting across saying, nah, you're going to have to stop now. It's only getting a teeny bit better and you're spending a lot of time on it. Diminishing returns. Oh, there, I see the one in the
Well,
chat.
let's first of all thank you
Yeah.
guys. From this is the 7th perspective seminar in the course that Megan's given. There has not been one that's so engaging with so much participation. I don't know if it's you guys or the chocolate.
Probably the chocolate.
But this was a very engaging talk, so let's thank Megan. Feel free to reach out. right?
Yep.
And
I am on LinkedIn and all those sort of things.
hey,
Yeah.
thanks so much.
That's okay.
Good luck with big homework, not do next week, grab a chocolate on the way out.
It's all right. Let me shut stuff down.